Hello students, I'm Dr. Jan, and as you know, this summer we are going to Argentina, and in Argentina I'm going to teach computer science to students there, and our wonderful TAs have prepared exams for students in Argentina. However, I secured my final exams in a very secure place that no one can find. Okay guys, the class is over, thank you.
Hey Nelson, can I talk to you?
Yeah.
So, bro, we really need to get this computer.
We need those exams.
I got no time. I'm not studying
I don't
for
know
this
what's
exam.
going. Yeah, I'm not going to the exams.
I'm failing the class, bro. Please.
Okay, let's talk later. We need to make a plan.
Yeah,
Okay.
we'll talk.
Okay.
I know her, and it won't be easy.
I know.
We need to devise a plan because the laptop will be somewhere hidden inside this
Yeah, it has
house.
to be like here.
Yeah. So, what do you think? You've been paying attention in the class.
I think we have to go for DFS. We name our vertices using numbers. Our goal is to find a way from vertex 1 to vertex 24 using a depth first search. First, we put node 1 on the call stack. We mark it as visited so that we don't accidentally reevaluate the node. Node 1 is not the one we're looking for. We move on to its adjacency list. We will agree that we will always move to the one with the smallest value. Next, we evaluate node 2. We mark it as visited and check if it's equal to node 24. Since it isn't, we place node 2 on the stack. We could comparing and calling DFS on each node, ending up at node 5. We mark it as visited, check if it is equal to node 24 and try and move deeper into the graph. However, the only connector node 5 has is node 8, which we have already visited. So what happens now? We have to do something called backtracking. Nodes 1, 2, 9, and 8 are still on the stack because they are part of a potential path. Once we hit node 5, though no other path exists, we have to backtrack to node 8. So we look at the next node in 8's adjacency list, but there are no more nodes, so we need to backtrack again. The next node in 9's adjacency list is 10. Once we reach node 4, we backtrack to node 1 and evaluate node 12. We visit, compare, and call DFS on each node, much like before. Only once we hit node 24, we reach our goal. Now, looking at the call stack, it contains a path from node 24 to node 1. We can begin to remove all our DFS calls from the stack and print off the values, thus giving us our path to the laptop.
Okay, I have finished the final exams for the students, so now I'm going to place these exams somewhere very secure. Now let me take a quick nap. Oh my god, where is the laptop? All my exams are in this laptop. I should find this laptop. Let me call the sheriff.
The sheriff is over here. Where is Jan's laptop?
Sheriff, I need to find these exams as soon as possible because I'm giving them. You should do your best search that you have ever performed in your career.
I'm really trying. I think I got it. I think. Yeah, we found his escape route. Now he might be in the city. So he's somewhere in the city.
Okay.
Right now, I'm writing the code for the BFS algorithm, and I think we should be there by noon. The breadth-first search is a fundamental search algorithm used to explore nodes and edges in a graph. It is particularly useful for one thing, finding the shortest path on unweighted graphs. It is more useful than the one used by Nelson previously because you don't actually get to explore all the nodes in a graph using a DFS algorithm. A BFS starts at some random node, let's say the pizzeria, and then explores the neighboring nodes first before moving to the next neighboring nodes, so the neighbors of the neighbors, and so on. To do that, a BFS algorithm maintains queues of which nodes it should visit next. Neighbors that have been visited are not added in the queue and are skipped. We repeat this process until we run out of nodes to add to the queue. The time complexity of the BFS, if the entire tree is traversed, is O, big O, V, where V is the number of nodes. E is the total number of edges in the graph. Defining it this way is useful because you don't necessarily have the same number of edges on every single vertex. Since each edge gets visited once, you get big O E complexity from that part. Then you add the big O V for visiting each vertex, so you get the complexity of big O V plus E in total.
Huh! I knew it! I found you.
No!
You have been
Wait.
uploading
I
Dr.
need
Jan's
exams the whole
exams.
time. No!